Okay, so we're gonna start with a couple practice with the solubility rules to make sure you guys feel comfortable with that. I had a few more I was gonna add to it though, so let me copy those over from the last class. Let's see if copy paste works. No, I didn't like that. Okay, I'll just write these in. Okay, so we're using the solubility rules to determine will these compounds be aqueous in water or solid. And I'm going to add a few more to the list just to make sure we get a decent amount of practice. Okay, so we did a few together last class. I want you guys to take a few minutes. Maybe in a couple minutes, I'll go through and write which rule would apply here so that you can, if you're stuck, you can use that. And I don't want to forget, I'm going to change that reading. Oh, 26 of you guys have completed it already, even though it's not quite due yet. That's good. Okay, so I pushed the chapter 6 reading to Tuesday because I'm confident we're not going to start chapter 6 on Monday. We'll have to finish out this one. And then chapter 5 homework, you can definitely get a good start on it this weekend. So that's due on Tuesday as well. But we will have done 3 of the 4 days. So I would highly recommend that you guys get a good start on the chapter 5 homework. Okay? The only thing we will not have covered is writing precipitation reactions. All right, I'll be quiet and let you guys finish this. that enough time? I'm not seeing any head nodding. Okay, just another 30 seconds or so. So I put up the answers already if you want to check what you have so far. And then the rule numbers, those are the little numbers on the side there. Okay, so the rules themselves are given to you, but obviously you need to be able to know how to use them. So too often people just assume they're on there, it's fine, but you have to be able to apply them and figure out how to like do all the exceptions and stuff like that. So if this is not adequate, there is some on the homework for sure, but seek out any additional practice as needed. Okay, so sometimes people, and I definitely am sensing that, whenever I start talking about the concept-based stuff, it's like, ugh. You may not love math, but people feel okay with math. They feel comfortable with it. But there is obviously a lot more to chemistry than just solving problems. We did balanced equations last time, but we were always given those equations. And now we're getting to the point where we actually have to be able to write them and predict the formulas on our own without actually being given those, okay? So this is part of that, being able to identify the state of an ionic compound. Okay, I decided that some of this is just too much. I'm not going to spend more than 4 days, and we don't have the time. So we're skipping that and this. I've already taken off the questions on the homework that were related to that. And this one, for some reason, is misplaced. Well, I think it's misplaced. So I'm going to come back to this in just a second. Okay, so we are going to talk about different types of chemical reactions that are occurring in aqueous solutions. So we've talked about the background of water solutions and what that means. We've looked at ionic compounds, specifically how they dissolve in water. And now we need to deal with the actual reaction that occurs. The thing that's nice about this is you guys have already done labs on both acid-base and precipitation. And gas-evolving reactions are pretty darn straightforward because they always produce a gas. So identifying them is pretty darn easy, okay? So we're going to start with acid-base today, which, like I said, hopefully it's not too crazy because you guys have had a bit of an introduction in lab. I know it's always like just frantically scratching the surface to try and get the lab done, but hopefully this will at least sound familiar, okay? So there's quite a few different ways to describe what an acid is. The two most useful ones are, do I have that written down before I rewrite it? An H plus donor produces H plus. Okay, that's one of them. Produces H plus in solution. And we're going to find out in a second that really it's better to consider H plus as H3O plus. So we'll talk about that in a second. And then the other is that an acid donates or gives a H plus away. So, hydrochloric acid, super commonly known acid, looks like this. And when it gets in water, it's actually a little bit odd because the hydrogen behaves a little bit like a metal. So when hydrogen is by itself, it has no properties of metal. It's not shiny, it's not malleable, none of that stuff. It's a gas. But when it's in an ionic compound, well, not an ionic compound, when it is in a compound, it's still a nonmetal. We still would call it covalent, but it has a lot of properties that are similar to an ionic compound. And hydrogen, if you notice, is in the first column with a lot of the metals. That's because in a compound, it can behave a lot like those metals. So if you look at sodium chloride and its behavior in water, it breaks down into Na plus and Cl minus. See, it looks almost identical. All right. The difference is that sodium doesn't do a whole lot to anything. If you have salt water and you pour it on the table, like, well, let's not say the table, let's say like the cushion or something, it's just pretty much going to sit there. Eventually the water will evaporate and it will be salty again. If I were to pour HCl, though, on the cushion, it's probably going to start eating away at the background. Okay? So sodium is fairly benign. H plus is what we consider to be causing all of the properties that we think of when we think of an acid. So acids and bases are both corrosive in different ways, meaning that they will degrade when they're on contact with something, they will degrade that thing. So whether you're talking about skin, or a material, they have the ability to corrode. Acids are sour tasting. We don't generally encourage you to taste your chemicals, but acids and bases are a common thing we find in nature. So lemons, tomatoes, vinegar, those are all examples of acids that taste sour. Bases, on the other hand, taste bitter. So chocolate, spinach, those are examples of bases in food. Bases are also like slippery. So soaps are an example of a base. If you accidentally get some hydroxide on yourself in the lab, you're going to feel that it's a little bit slippery. Okay? All right. So the thing that's responsible for that acid behavior is the H+. So the more of that H+ we have in water, the more acidic that solution is going to be. Now, when it gets into water, it doesn't really stay by itself. If you remember, let's pull up in the picture this one. When we get sodium in water, it doesn't really stay by itself either, right? It gets surrounded by water molecules. And so the H+ behaves a little bit like that. The way that we think of it is that it actually bonds to the water molecule itself, or attaches to the water molecule. So you can see here's a bunch of water molecules, and here a hydrogen that was released from an acid came along and attached itself to a water molecule. So sometimes people will refer to the acid donating its proton as just H+, being the product, but a lot of the time we will think of it as H3O+. So you can see down here, the equation is written a little bit differently. And I prefer this method. Now we're looking at the products being H3O+ and Cl-. It's the same thing. It still gave up that H+, it's just that now we're showing it attached to water. The reason why I like that better is because we can use this idea of acid donating its hydrogen or giving its hydrogen away. So in this example, it gives its hydrogen away to the base or to the water to form H3O+. The reason why this is useful is because when we start talking about acids and bases neutralizing, it's really easy to think of the acid just giving its hydrogen away to the base, and then the base accepts that hydrogen. So acids, we'll talk about them as donating the H+, bases, we'll talk about them as accepting the H+. Okay? All right. Let me come back to the polyprotic acids. Like I said, this guy's a little bit out of order. All right, so of acids, there are really only 6 that you guys will ever encounter that are considered strong acids. A strong acid simply means that whatever molecules you put in there, those are all going to break apart into H+ and the thing that they leave behind, Cl- in this case. So if I throw 4 units of HCl in here, I'm going to end up with 4 units of chlorine, 4 units of H+, and nothing else left over. Okay? If I take a weak acid, which is anything other than those 6, any other acid other than those 6, it's not going to react completely. Some of the original acid will stay put. It will keep bonded to that H plus and not have any effect on how acidic the solution is. So if I stick some of those units in water, I am going to make some H plus. This one's really hard to see. So if you can tell, this is one where it didn't. This is the hydrogen that it would have given up. We call that the acidic hydrogen. So you see there's other hydrogens on this molecule. The reason why we write them separately from this one is because those guys will never be given off as an acidic hydrogen. Only that one will. So we write it in a different place to kind of indicate that. So that's this hydrogen here. This acetic acid, so acetate ion with a hydrogen, this acetic acid is still acetic acid. It hasn't given up that H plus. This one, on the other hand, you can see those 2 oxygens, one of them is missing that H. It's right here. So it has dissociated or come off of the acid, whereas some of the molecules don't. So there's another one there. I think it's probably come off that one, it looks like. Yeah. So this one has lost its hydrogen and it's there, whereas all these other molecules are still intact. They haven't broken down. And this should feel a little bit weird because never before have we talked about a chemical reaction that doesn't go to completion. Like it doesn't finish and all the products turn into reactants. Okay? Or sorry, all the reactants turn into products. I could like kind of feel my caffeine levels dropping. I feel like there's some chemistry way that I should be thinking of that, but mixing up words is definitely a sign. Okay, so like I said, every acid that's not one of these 6 is a weak acid and will not completely break down. So if I have 1 molar HCl and 1 molar acetic acid, this is going to be way more corrosive than that one because it has more H plus that it's forming. Even if there's 1 mole of each in a given liter, this one's going to make 1 mole of that. That's going to make a fraction of a mole, okay? So that one's going to have a lot more acidic, corrosive properties. The way we represent that is with this double-headed arrow. That's how we represent that it is not going to completely react. So they're saying some of it's still going to be that reactant. When we write it, hand write it, a lot of the times we'll draw it like this. So it's like a cut off half arrow, whatever. Some going forward, some staying backwards as the reactants. Okay. The last little thing as far as like definitions are polyprotic acids. So these are ones that have multiple hydrogens that they can donate. Sulfuric acid, which is one of the 6 strong acids, is one of these. So H2SO4, both of those hydrogens can be donated, and or the other way we would say that is they're both acidic hydrogens. So not only is sulfuric acid strong, like HCl, so it completely reacts. So the hydrogen goes from here over to there. The water turns into H3O+, and the sulfuric acid turns into 1 less hydrogen. Remember that hydrogen left its electrons behind, and so that turns into HSO4-. So that happens completely because it's a strong acid, but now this guy can go on and react even further and make more H3O+. So that's why sulfuric acid is like considered the scary one, because not only is it strong, but it also has 2 protons that it can donate. Another common one you'll see is phosphoric acid, but that one's not a strong acid, but it does have 3 protons that it can donate. But they don't happen completely. And every one gets weaker and weaker. I think I just said it, but proton is the other term that you'll hear people use for H+, because hydrogen is a proton and an electron. So if it's lost its electron, it's just a proton. So we'll often refer to acids as proton donors instead of just H plus donors, because that's kind of cumbersome to say, I think. Okay, so it's a hydrogen without its electron. It left its electron behind with chlorine in this example. All right, I feel like we need to take a little bit of a break. So why don't you, I'm going to give you an acid. Oh, there's a list. Where did it go? There it is. I want you to do formic acid and hydrofluoric acid, and I want you to write the reaction in water for those two acids. Okay, so formula of formic acid plus water, tell me what the products are. I'm going to draw these both as those double-headed arrows because they are both weak acids. Probably the biggest mistake people make with this is the charge. So you have to recognize that the thing you're leaving behind, it kept the electron from the hydrogen. And then because the hydrogen is going to neutral water without its electron, it causes a positive charge. Okay, so this is what your formulas should look like, your reactions. It's pretty standard because if it's reacting with water, you're always going to be producing H3O plus, and then whatever's left behind when that hydrogen leaves. Acids are quite a bit easier in that way. Bases, there's kind of two versions of them. Okay, so let's talk about bases now. There are two different types. Obviously, there are two different types of acids too, strong and weak. The strong bases look very different than the weak bases though. So the strong bases are listed here. So it's actually all of the soluble hydroxides. So do you remember we said that lithium, sodium, potassium, and ammonium no matter what they're with, they'll dissolve. So it's all of those with hydroxide. Those are the strong bases. Now, some people will say that some of the 2A hydroxides are strong bases. I do not subscribe to that opinion, like this one here, because they won't dissociate completely unless you add an acid. And to me, that doesn't mean that they're strong. But you might hear that. I can't remember what your textbook says. It literally, someone was like, no, but are they actually? And I'm like, well, like, depends on the chemist you ask. I would say no, they're not. Because if you stick them in water, there will still be some solid at the bottom. So what do we mean when we talk about a strong base then versus a weak base? So one of the definitions of an acid is that it produces H plus or H3O plus. Remember, H plus, we often will call that a proton. H3O plus, we'll often call that hydronium ion. So I'll probably stop saying the formulas because it's annoying. So I'll say it produces hydronium ion, okay? So bases can be defined as producing hydroxide ion. Or another way we can think about it, and this only, not totally, okay, it mostly works for the weak bases, but we can think of them as H plus acceptors. So we said base or acids donate H pluses, bases accept the H pluses. So they're opposites of each other. So the way that the strong bases will, and really any hydroxide salt, the way that they will produce hydroxide in solution is just by dissolving, just like sodium chloride would. If sodium chloride goes into water, it makes sodium plus and Cl minus. If sodium hydroxide goes into water, it makes Na plus and OH minus. It's just that the anion, OH minus, has particular properties called base properties that make it important, okay? So anytime you have a salt, and really it's the 1As that matter, that has hydroxide in it, it's going to produce hydroxide just by that salt dissolving. Weak bases look a little bit more like the acids do. So now, instead of the hydrogen going from the acid to the water, what's going to happen here is that the water, one of those hydrogens, goes to the base. Okay? So that's why it's accepting a hydrogen. So I'm going to go like this. And if I have, let me actually draw a picture. I didn't do this in the other classes, but maybe it's helpful. So here's water. And remember that these represent 2 electrons. One from the oxygen. Oxygen has other electrons too, but one from the oxygen and one from the hydrogen that are being shared. This goes away, okay? It leaves its electron behind. So now you're creating an imbalance in the number of protons and electrons, and that's why the OH has a negative charge. And also why when the hydrogen goes to NH3, it doesn't bring its electron along, so it makes an uneven number of protons and electrons, and that guy has a positive charge. So when you do bases, you're always going to see OH minus on the product side, and then whatever's left over is going to take that hydrogen, and that's what you're going to have on the other product. So what do you keep stuck in your head? Acids donate H plus, bases accept OH plus. H plus, ignore that O there. Another version, acids produce H3O plus in water. Bases produce OH minus in water. And if you can keep that and then apply it when you're writing reactions, you'll be fine. So a lot of the time, if you can just simplify the concept into a couple different sentences there and then repeat them back to yourself as you're actually applying it to stuff, that can be helpful. Obviously, there's nuance in how you apply it. Okay, so those strong bases, other bases will be weak bases, and that means that they will not react completely. So when you stick ammonia in water, some of it's going to stay as ammonia. Some will produce ammonium and hydroxide. A lot of it's going to stay as ammonia, though. Okay, everything up to this point, we've been looking at an acid in water and a base in water. Maybe I should make you write another base in water, actually. I'm going to have to come up with it on my own. Okay, let's do one more. I'm going to pick it. I always like to think of one that doesn't have charge, though. No, I don't care. Okay. So I want you to write the reaction of this acting as a base. So it's a weak base, but I want you to show me what the products would be. So think of your two rules. Bases accept H+. Bases also should produce OH- in solution. Okay, so OH- should definitely be there because it's a base acting in water. And then if H2PO4- is accepting a hydrogen, it should turn into H3PO4. Now, if you remember, we talked about H3PO4 already, phosphoric acid. That's the interesting thing about acids and bases, is like there's a very close connection between, we call them the conjugate acid. So this would be a base and this would be its conjugate acid. They're like a pair that are just differing by that H+. We'll get into this a ton more in Chem 2. So we have to spend a lot of time, if you're taking it, so we have to spend a lot of time talking about this idea of weak reactions or reactions that don't go to completion before we can do some of the more complicated things with with weak acids and bases. Okay, so acid and water, base and water is what we've done so far. Now we want to look at an acid and a base reacting. And if anything, this is a little bit easier because you kind of eliminate the charges because you have an acid that's going to donate H+ and a base that's going to accept H+. And if it's a strong base, you end up making water because you're basically taking, I didn't do that on purpose, you're taking H+ and OH- and they're kind of pairing up together. So on HCl, you see that hydrogen moves over to the OH-. It's donating. The base is accepting. So the H and the OH- turn into water. That was supposed to be me showing that those guys turn into water. And then what's left behind is the Cl- from the acid, the Na from the base. So it's not wrong if you leave this as just Na and Cl. Anytime we have a plus and a minus like that, we very often will just write it together. like if they're both a metal and a nonmetal. So not if you had like H3O plus and Cl minus or something, you would not write those together. But if they're just a regular ionic compound or components of an ionic compound, then we might write those together. So this would be considered a neutralization because if you have equal amounts of these, it's just going to make water. So think of like baking soda and vinegar. When you mix those together, they react. The stuff you end up with at the end is pretty much just water and some salts. Okay, so I want you guys to write a couple of those reactions now. Start with this one because this one's a little bit trickier. So hopefully you guys can see that even though these are concepts, there's still a lot of doing. Just because it's not math doing, they're still doing. You have to name things. You have to categorize whether they're soluble or not. You have to write reactions. You have to pay attention to where the charge goes. So it's not math, but it is still doing. So understanding the concept behind the math is important, then do the math. Understand the concept behind this, and then do the whatever it is. And those are the things that are going to take a lot of practice. I will go ahead and put states on these. This isn't quite as important here as it's going to be in the precipitation reactions, but it's good practice. Okay, just one more minute and then we'll talk through that. Okay, so bottom one first. Acid donates, goes to the base, that makes water. What's left behind is this, but it's negative, and this, but it's positive. So you can write them separately, that's fine, but like I said, when you have a positive and negative that are like the components of an ionic compound, you're gonna see them written together. So like if you were the one doing the writing, that's fine. Just recognize that that's okay, because you're gonna see other people write it like that, like the book, or answers on the exam, or something like that. On the one on top though, the thing here that you need to realize is that there's actually 2 bases, 2 hydroxide units for every 1 barium hydroxide. So although you're donating an acid or a H plus to it, you're actually going to need 2 for every one of those, and then you'll make 2 waters, okay? Because you've got 2 hydroxides. So if you want to think of it this way, this guy is basically like Ba2 plus, OH minus, and OH minus. So how many HCl's do I need with those OH minuses? I need an HCl for each one. So I need 2 HCl's, then I'll make 2 different waters. I'll have 2 chlorines left behind. Put that there. And then the barium, which should make sense because we know barium is a 2+ ion because it's in the second column. Ooh, it's like all coming together, right? Very first unit, I feel like, was when we talked about the charges that elements will form. Maybe it was the second. No, it was the first. So barium 2+, you knew it was 2+ because of the periodic table, also because hydroxide's -1 and there's 2 of them. So then when it combines with chlorine, it's going to be BaCl2, which makes sense because we have 2 chlorines there. Okay, so this should feel like a lot of different things coming together all at once. There's definitely going to take some time for all of them to make sense because you're putting together a lot of different components. Rest assured that the exam is multiple choice. That's a little helpful for you. If you miss one teeny tiny thing, assuming that I didn't intentionally put that teeny tiny thing as the other option, then you should be okay. Okay, last thing, you guys already did a titration in lab, so this is kind of a recap. When you do a titration, it doesn't matter where the acid and the base are, but you have acid in one thing, base in the burette, so maybe the flask and the burette, and you're going to add base until you completely neutralize that acid. And for most things, that's going to be a 1-to-1 ratio. So just like we saw, most acid-base reactions are coefficients of 1, meaning you need to have the same number of moles of acid as you have of base. In this example, it was not. So there are a few where you have to be careful about that. But the ones we're going to give you for now in this class are going to be 1-to-1 ratios. So kind of the key point is that at the end point, moles acid equal the moles of base. And it looks exactly like the dilution equation. It's sort of the same, but we're just going to say MAVA equals MBVB. Okay? And that can help us to identify questions like this, where it asks us what volume of the base is required to reach the end point or the equivalence point. Okay, so go ahead in the last couple minutes and solve this one using that equation. You do not need to move it out of milliliters. You can leave it in milliliters because they will just cancel each other out. And if you finish before everybody else, you could write the balanced equation too. So you might have been able to do that one in your head since the hydroxide concentration is half that of the acid, you're going to need twice as much volume. Okay, so that's the extent we'll do of acid base, and we'll do precipitation reactions on Monday. Yes.
So when we were going over these ones,
Mm-hmm.
I got confused because I didn't know that we can like separate this. 'Cause
Yeah.
I was going.
You're gonna like pair those up and then pair those up. That's great, because you're gonna see this written like that more often. It's just that when something is soluble, right? So all potassiums are soluble, then really in water, they're gonna break apart, right? Like when we see the picture, we show them as separate. So that's why you can do that, only because they're dissolved into water. Now, if you made something, this wouldn't happen in an acid-base reaction really, but if you made something that wasn't soluble, like lead iodide, let's say, or lead chloride, then it would actually be a solid, and then it's not appropriate to separate them. So I would never give you both of those as options on the exam.
Now, is it going to be easier to just like write it out this way?
No,
or just go
I like
straight?
this. This is better.
Okay.
That is how you're going to see it in the textbook more frequently anyway.
Okay.
So, good job. Yes, I didn't. I keep bringing it and I keep not handing it out. So, thank you.